Just as water exists in different phases, solid, liquid or gas, so does nuclear matter. The temperatures and pressures at which the various nuclear phases exist can be illustrated on a phase diagram. At everyday temperatures, nuclei behave like liquid drops. As the temperature and pressure increases, they boil to form a hadron gas. Finally, at temperatures 100,000 times hotter than the Sun, and at densities 10 times higher than that of ordinary atomic nuclei, the hadrons melt to form a quark-gluon plasma. To explore the nuclear phase diagram, nuclei collided at various energies to create hot, dense nuclear matter, which is then analysed. The results might give scientists an idea, for example, of the conditions in a neutron star when it collapses to a black hole. An important goal is to understand the early evolution of the universe. About 10 microseconds after the Big Bang, matter would have existed as a plasma of free quarks and gluons, which combined into hadrons as the universe cooled. Many questions need to be answered. Quarks are almost massless, and researchers hope that studying the transition to a quark-gluon plasma will shed light on how hadrons like the proton acquired mass. The compressed baryonic matter (CBM) experiment at FAIR will map the nuclear phase diagram around this transition, while the ALICE experiment at CERN's Large Hadron Collider will collide nuclei at unprecedented energies that will allow scientists to explore the quark-gluon plasma phase. Nuclear systems play a significant role in the quest to obtain a complete picture of the building blocks of the universe. They're described by the Standard Model of Particle Physics, which comprises 2 families of matter particles, the 6 types of quark and 6 lighter particles called leptons, the electron, muon and tauon and their respective neutrinos. 4 basic interactions are known: electromagnetism and the weak force, the strong force, and gravity, which is not yet part of the Standard Model. The first 3 forces are mediated by known particles, the photon, the W and Z bosons, and the gluon respectively. A major goal of physicists is to devise a unified theory of the basic forces and particles that extends the Standard Model to account for their origins in the first fraction of a second after the Big Bang. One way to search for evidence of the Standard Model extensions is to look for tiny signature deviations in the nuclear processes, such as radioactive decay. An important concept in exploring these extensions is symmetry. The universe started in a highly symmetrical state, but as it cooled, various symmetries were broken, generating the matter and force particles we have today. One symmetry of key importance is that between matter and antimatter particles with opposite charge. It can be investigated in several ways, including looking for minute differences between the properties of hydrogen and antihydrogen. Many of the experiments require very precise measurements at very low energies, which a new generation of facilities will enable. These include low-energy antiproton facilities such as FLARE at FAIR and the ELENA upgrade to the antiproton decelerator at CERN. Nuclear physics and the tools developed to study it offer a wealth of enabling knowledge and innovative technologies that are benefiting society in crucial ways. Subcritical reactors based on new accelerator-driven systems and nuclear fuel cycles could provide sustainable energy that's almost carbon-free, as well as being used to transmute radioactive waste into less hazardous material. In the health sector, nuclear particle therapy and radioisotopes are increasingly being employed as both diagnostic and therapeutic tools, particularly in cancer treatment. Nuclear physics has also generated a large toolbox of analytical techniques using radioactive isotopes and ion beams for applications ranging from environmental monitoring and climate change studies to the dating of geological, archaeological and art objects. National security and border control have become key issues, and nuclear techniques are playing a major part in detecting or tracking strategic nuclear materials and explosives. To tackle future scientific challenges, a network of nuclear physics facilities offering exquisitely tailored, intense particle beams is essential, along with sensitive methods of identifying and characterizing the products of interactions. The new FAIR facility to be built on the GSI site will be Europe's leading centre for research into strong interaction physics. A key feature is the production of a unique intense anti-proton beam. FAIR's complex accelerator system will also generate a wide range of high-precision, high-intensity beams of stable and unstable nuclei. The new Spiral 2 accelerator at Genil will produce exotic nuclei at extremely high intensities. FAIR and Spiral 2 employ different but complementary setups to produce such beams, the in-flight and ISOL systems. Such facilities require highly innovative technologies. These include improved accelerator components such as new ion sources, targets, accelerating devices, magnets and detectors. The advanced instrumentation can then be transferred to benefit other fields, particularly industry, health provision and energy generation. Many young researchers trained in designing and developing these new technologies go on to employ their skills in industry. NuPECC is presenting a range of recommendations of how to best develop the field of nuclear physics in Europe during the next decade and beyond. These cover FAIR with its 4 pillars, the PANDA experiments, the NuSTAR facility, the CBM experiment, and the Atomic, Plasma and Applied Physics program, APA. And Spiral 2, which will provide complementary high-intensity radioactive and stable ion beams. Major upgrades of complementary large-scale nuclear physics facilities, the radioactive ion beam facilities at High-Isolde, at CERN, and SPARES at INFN-LNL. Spiral 2 with High-Isolde and SPARES will eventually lead to the ultimate ISOL facility for Europe, EURISOL. The construction of the Agatha gamma ray detector to be used at these facilities and the new superconducting LINAC to provide high-intensity stable beams at GSI. Upgrade the nuclear beams program and the ALICE detector at CERN. Strengthen theory support to experiment and invest in high-performance computing facilities dedicated to nuclear physics projects. Fully exploit and upgrade existing large-scale research infrastructures around Europe and smaller-scale national and university nuclear physics laboratories. Develop the nuclear physics skills base in particular regarding energy generation, medicine and security, and the development of technologies that will also be used in other fields. Continue scientific and technical assessments for building new large-scale nuclear physics facilities in the future, such as the Electron Nucleon Collider, ENC and EURISOL.